volume plus 49. And 0 to infinity, y equals negative y over 7. Again, integrating by parts, negative 7, y into negative y over 7, plus 7, infinity. Again, that gives you 0. You compute this. Oh, 749, so 107. Okay. Calculations are working out really easy. Integrate that, you get e to the negative y over 7, negative 7, 0 to infinity. When I plug in infinity, that's just 0, minus negative 7, e to the 0, that's 1. That calculation is actually not that bad. The nice thing with the integration by parts, the nice thing was that these terms always gave you 0, so you didn't have to keep track of them as you continue.
I know why your coefficient jumped to 98. Why did it go back to 49?
Because I had a 2 here.
Oh, okay. Got it.
So how many points would you get if you just stopped?
Stopped here and just gave up. It depends on how many points that the problem is for, but I mean, I think it's definitely worth like 2 or 3 points, if you go through that computation.
But as a strategy, we should probably stop, go to the next problem, come back and finish this up.
Yeah, it makes sense to first set up your problems, but if most of your problems are going to involve integration, then you're going to be leaving everything halfway.
Right.
So, but yeah, I mean, the idea is if it looks like it's going to be a complicated computation and you really don't have the time, the better bet is to work out and start and set up as many problems as you can. Okay. So, yeah. So computations, if you think it's going to take too long and you're going to mess it up, set it up, come back to it later. But I think, your computations will be simple enough that you should just work it out and then move on to the next problem. But again, if you feel you're going to take too long with the computation, just go to the next problem. Covariance, again, this is just a formula. Expected value of y, and here's where if you compute the expected value of x, expected value of y earlier separately, that might have helped because then you can just modify that out. If not, then you it might be a good idea to do these 3 computations separately and then just put them in together later on, because otherwise you will have to keep writing down everything in every step. So it's probably better if you do this computation first, so you finish that up, do this computation and this computation, and then pop that in there. So now this is only if you're running out of time, because finally this is just a computation problem, so quite a lot of points will go towards actually getting an answer. I would definitely want to see this formula. I want you to see this, I want to see this thing set up, definitely. This set up also. So you could either write it like 0 to infinity, 0 to y, x times the joint density, right? Or dx dy, whatever. Or if you want to do this calculation first on the side, so this is going to be, you integrate out your, so in this case, so one would go from x to infinity. Infinity. Right. So you first compute that, and then when you wrote this down, you would instead write it like this. 0 to infinity, or negative to infinity, x. This. So you have to break it down into several computations. First compute this, then compute that. Same thing with fy. So this is going to involve several steps. Now you integrate first, integrate out your x. So x goes from 0 to y. So you would compute that, and then you would write out y to infinity by. So each of these computations will take several steps. All right. I'm just going to move on to the next problem. Yeah. Okay. All right. So for those calculations, remember you got to do all those steps. So it's quite a lot of calculation. Okay. The next problem is 6. So the question is, x is normally distributed, y is normally distributed, and x.
That's
So-
x to infinity.
Wait,
The bottom integral.
this one? Yeah, x
No,
goes
over here.
here?
Or
Marginals.
sides you,
The marginals.
Here? Yeah, here from x to infinity, yeah. So you're integrating your y from x to infinity. In that problem, your y has to be greater than x. Alright, so in a problem where you're asked to prove something like this, show that the normal distribution, there are a couple of ways you can think of trying to prove the distribution of this. One is you could try and calculate the distribution function of this. Okay. So you could try doing that, but I mean, hopefully you realize with normal distribution it's going to be a little complicated.
Both those marginals are with respect to y.
No, so this marginal is the marginal density for x, so I integrate from x to infinity. This is the marginal density for y, I integrate from 0 to y.
And they're both dy's.
Oh, yeah. The other one is integrated. Yeah. This is, I integrate that d. So actually this is very easy to compute, right? You just be x times that, so you just get y e to the negative y over 7 over 5. So the second one, I'm integrating out my x, so I integrate with respect to x.
I'm sorry, are we going to have proofs of this exam?
No, I mean the proof would be like a problem like this, which
Like this,
basically involves a computation.
Right.
So, okay, so do not try and use this. Now, one hint is you know that it's independent, And for things like normal distribution, Poisson, you know the moment generating functions. Okay? So it would be best to use moment generating functions to prove this problem. Okay? But technically, you could try and first prove this. Okay? And then say, oh, ax plus by is equal to z, but this is going to get very complicated. Okay? So the best way to do this is, let's look at what the moment generating function of ax plus by at some point t. So the moment generating function of this random variable. So this is simply, by definition, is ax is t times ax plus by. Tax equal tby. I've given you that x and y are independent, so this is just all right. So this looks like the moment generating function for x at the point t times a times the moment generating function for y at t times b. This line. Now what's the moment generating function for x? X is normally distributed, so the moment generating function for x is e to the mean of x times this quantity, so at times the mean of x plus 1/2 a squared t squared times the variance of x. Okay? The generating function of y at tb is e to the t times b times the mean of y plus 1/2 t squared b squared the variance of y. So that's just the form of the moment generating function. So it's a good idea to either memorize these moment generating function forms or have them on your formula sheet. So in the exam, I would expect you to know the moment generating function for all those that we covered. Normal, Poisson, binomial, what else?
Binomial, Poisson, exponential, we covered.
I covered exponential? Okay. Yeah, so all those, right. Okay, so let's simplify this, because what did you want to prove? You wanted to prove that ax plus by should have what form? So if you simplify this, you get collect terms of, you get t times a mu x plus b mu y, and you get,
Plus you,
let's see, 1/2 t squared a squared sigma x squared plus b squared sigma y squared. Now, this looks at the moment generating function of a normal distribution with mean. The moment generating function is e to the t times the mean, so then this is the mean, plus 1/2 t squared times the variance, so that means that must be the variance. Okay? So therefore, this is the moment generating function of a normal a mu x b mu y with variance a squared sigma x squared plus b squared sigma y squared distribution. So what have we proved? We've proved that the moment generating function of ax plus by is the moment generating function of a normally distributed random variable this. So therefore, by the uniqueness of your moment generating function, therefore ax plus by is normally distributed. part B basically uses this result, that if you take linear combinations of independent normal random variables, you still get independent normal random variables. And the means are just the linear combinations of the means. The variances are, you just take coefficient squared. Part B. So students' grades are normally distributed with mean 72, variance 25, the average grade of a class. So in this problem, we say let xi be the grade of ith student. And you have altogether 25 students. Now you know that each of these xi's, this is the information given to you, is normally distributed with mean 72 and variance 25. And here's something that, since it's not given, you can just say, we're assuming xi's are independent. Now if you've assumed that xi's are independent and you know they're each normal, if I look at the class average, what is the class average? If I denote it by capital X bar, it's, that's the class average, right? So this is the class average. And the question asks, what's the probability that the class average, X bar, is greater than or equal to 75? So now here's where I'm going to use part A of my problem to figure out what the distribution of X bar is. Although I have mentioned this before in class, but so X bar is basically, you can think of writing it as 1 over n x1 plus 1 over n x2 plus 1 over n xn, right? It's just x1 plus x2 divided by n. So this is just ax plus by plus cz, etc. So by part A of this problem, this is just going to be normally distributed with mean 1 over n, the mean of x1, which is 25. What am I n in this case? 25. So 1 over 25, the mean of x1, which is 72, plus 1 over 25, the mean of x2, 72. So basically, I'm going to get 72 plus 72 plus 72 and 25 times divided by 25. So I will just get 72. So this is essentially using part A. And the variances also are just going to be, the way that variance works is you take the coefficients, you square them. So you get 1 over 25 squared, the variance here is 25, plus 1 over 25 squared, the variance here is just 25. You do this 25 times, so I have 25 times 25 over 25 squared. So I get, so I just get this variance to be 1. So remember, with the variances, it's the coefficient square times the variance. Now add that 25 times. Okay. So I've got the mean to be 72, the variance is 1.
I'm sorry, what does this, I understand the 1 over 25 squared. What does the 25 represent?
Oh, okay. So actually a little confusing now since the mean n and the variance is the same. But basically it's so let me say a1, x1, a2, x2. Variance of x1, let me just call it sigma 1 squared. squared, right?
Okay.
Now, A1 square, A2 square, they're all, in this case, they're all 1 over n, right? Because I was looking at x1 plus x2
Right.
over n. So each of these is 1 over n squared. 1 squared, 1 over n squared, sigma 2 squared. So it was just sigma 1 squared plus sigma 2 squared plus sigma n squared divided by n squared. Each of my sigmas were the same value, right? So say all my sigma i's were just sigma squared. Then that means I've added sigma squared how many times? N times. So n sigma squared over n squared, which just gives me sigma squared over n. And this is something we've also proved earlier, that the variance of x bar is just going to be the variance of each of these xi's over n. So here your sigma squared is 25, your n is 25, so you get 25 over 25 is your variance, and that's this one. Okay. So we have, so we now know that x bar is normally distributed with mean 72, variance 1. So what is that probability? X bar minus, so this is a normally distributed random variable. You're looking at the probability of a normally distributed random variable. You know how to calculate these probabilities. The way you do that is you standardize, you normalize it so that it's standard normal, and then you use your tables. So it's x bar minus the mean, which is 72, divided by the standard deviation of that, which is square root of 1, greater than or equal to 75 minus 72, divided by the standard deviation of that, which is square root of 1. So you get, this is standard normal, greater than or equal to 3. So what's this probability? I think it should be something very close to 0. So it's 1 minus
60.
Yeah. Probability C less than 3.
So you're saying the variance is 1 now instead of 25?
Yeah, the variance of x bar. And what is x bar? X bar is summation xi over n. The variance of x bar, if x has variance of x, each of these xi's is sigma squared, variance of x bar is sigma squared over n. So that was something that we've also proved earlier. So if your sigma squared was 25, your n is also 25, 25 over 25, the variance is just 1. So now there's the variance of the class average. What does the variance of the class average look like? All right.
Are we going to be able to make it through all these?
We just had 2 more problems to do. I think we did the others earlier.
Yeah, I'm sorry, wouldn't it be less than or 3, so wouldn't it be 5, 3? Don't we have to do 5, 2, 2, or no? We don't have to include 2 and 1.
I'm going to do the other.
I'm sorry, I didn't hear what.
Because it's 1 minus the probability that Z is less than 3. So wouldn't, like we have 5, 3, but then wouldn't we have to encounter 5, 2 and 5, 1, 2, or no?
No, 1 minus, so what's 5, 3? 5, 3 is probability Z less than or equal to 3.
Yeah.
Okay. Phi of A is probability Z less than or equal to A.
To A. Okay.
Isn't 5, 3 almost 1 here?
Yeah, so that probability is going to be something like 0. Okay. Now see, I think I've already stated before that the average of normally distributed things would be normally distributed, the mean stays the same, the variance becomes sigma squared divided by n.